Hey everyone, so today I'm presenting the paper, What does a platypus look like? Generating customized prompts for zero-shot image classification. So it's a very simple idea, but sometimes the simplest ideas can go a long way. So I think that's one of those papers. So before going into the model, I'd like to just give a brief intro clip. So clip is a open vocabulary vision language model that tries to match image captions to the respective images. So of course we use contrastive pre-training using image text pairs from the web. So the image is passed into image encoder, the text is passed into text encoder, and we minimize the distance between the similar classes and maximize the distance between the different classes. So now how do you use this for zero-shot image prediction? So let's say you have a bunch of classes. Now you give these natural language labels. So for example, in the picture you see plane, car, dog, and you give a clever prompt. So the prompt is generally a photo of and the object, which gives passed into text encoder, and you use some similarity measure with a picture, which the embedding of the picture. So now that brings us to the motivation, which is how can we best represent an image category through natural language prompts? So, I mean, Clip and most derivatives of Clip nowadays use this standard approach where you handwrite a number of prompt templates, like so we saw in Clip, which is a photo of a category, and compile a natural language label for each category. And you fill in that category in each of the in the prompts. And you match the image embeddings to the nearest set of prompt embeddings to get the final class. So that comes with three basic drawbacks. So the first thing is that the prompt template has to be handwritten. So let's say you have a new data set, you need to write a specific prompt for that data set. So even just doubling the number of prompt templates like takes twice the effort. And the second thing is that it must be general enough to apply to all image categories. So for ImageNet, which is very diverse, let's say you use the prompt template, a photo of a category, but now you want to use something more informative, like you add in a type of aquatic mammal. This is useful information, but it's no longer relevant to other categories. And the third thing is that high performing prompt templates generally require prior information about the contents of the dataset. Again, in ImageNet, if you see a black and white photo of this is not, the template is not generalizable to other dataset. So what CuPL tries to do basically is very simple solution, which you couple a large language model or LLM with the zero-shot open vocabulary image classification model. Now, this seems like a naive approach, but it does three things. So it generates prompts for each of the image categories in the dataset, and it allows generation of arbitrary number of prompts with a fixed number of handwritten sentences, which I'll elaborate later. And it generally contains more rich visual descriptions while still remaining zero shot. Right. So here's one example of CuPL. So with the platypus example, so you give this prompt to the large language model, which is what does a platypus look like? Now, GPT-3 here says platypus looks like a beaver with a duck's bill, right? And you have multiple prompts like this, which are fed into a text encoder. And finally, later, when you give a picture of platypus, it matches it to one of the imaging embeddings which you have. So just some terminology here. So there are two types of prompts here. So the first is LLM prompts. So these are prompts which cue the LLM to generate the descriptions of the dataset categories. Now these prompts don't actually describe the object itself, unlike what is used in Clip, but rather just prompt the description of an object. So you can see here one example, what does a lorikeet look like? And the second is image prompts, which are actually describe a category. So you can see which the first one, a lorikeet is a small to medium sized parrot with a brightly colored plumage. And these are just the visual some photos of that. So there are two steps. So one is generating custom prompts and utilizing the custom prompts. So in the paper, GPT-3 is the LLM used. So now there are some custom LLM prompts constructed, but the point is that when you use the LLM, you need significantly less number of image prompts than what you use for Clip. So in the paper, they use 5 LLM prompt templates by hand for ImageNet. And for each LLM prompt, you use you generate 10 different image prompts. So for the image, that comes to around 50 image prompts per image category. And while generation, you use each prompt has a maximum of 50 tokens, but generation is halted early if it produces a period. And for more diverse image prompts, you use a high temperature of 0.99. So the second step, you utilize the customized prompts. They still use a clip backbone with a vision transformer as the open vocabulary model. And the sentences outputs of GPT-3 are embedded with the clip text encoder. And to get the category representative embeddings, I could call they're averaged and normalized. So 50 for ImageNet. And for classification, again, you use cosine similarity between the image embedding and the text embeddings. So in the paper, they studied two settings of CuPL, as they call, which is kind of a trade-off between accuracy and hand engineering. So the first one, which is CuPL single prompt, you use one single handwritten sentence for all the data sets. So here you can see the LLM template is of the form, describe what a type of dash looks like. So like we have data sets for like pets, aircrafts and all that. So if you have a specific type of data set, the type is filled in. But for something more general, the phrase a type of is omitted. And the second one is full prompt CuPL, which you use between 2 to 9 LLM prompts, which generate between 20 and 90 image prompts per category. So this is what the example prompts are. So you can see how basically CuPL cuts down on the number of prompts is. If you see the right-hand side for ImageNet, this is just a couple of prompts which are used, and like this, there are around 80 prompts or so for ImageNet, whereas for CuPL you use only 5. And for some of Clips derivatives, you need prompt engineering or so, but there's almost no prompt engineering required for CuPL. And some image prompts generated from the GPT-3 for go-kart you can see below. So they look pretty diverse. So this is the result. So they compared the standard is the clip model. So they say they get a 1% improvement on the image set, which they say is a pretty big deal. So 1% increase there. So you can see the different types of data set. There's a cars data set, a food, aircraft, pets, and some other stuff. So you can see the top right corner here. So the number of handwritten prompts for which need to be customized handwritten are 97 for clip. 1 if you use the CuPL single setting, and 25 if you use the full setting. Right. So again, I think in most we again see the performance of CuPL with model scale, which is basically you adjust the clip model size with VIT base 3216 and VIT large, and there's a pretty linear increase in that. And the second one is the GPT-3 model scale. So I mean the names are there, but the rightmost, generally the largest scale, gives better for higher accuracy. And yeah, so this is also with the number of prompts. So the first one is the number of LLM prompts. So you can see that, okay, so the blue line is basically clip, and that using one LLM prompt for CuPL still outperforms the baseline. And the second one is with the number of image prompts. And you can see that for around 25 image prompts, which is basically 5 per LLM prompt for this for the ImageNet dataset, it outperforms clip. Again, this is with the performance with the diversity of prompts. So if higher the temperature, basically the likelihood of selecting lower probability tokens increases, because you use an inverse power or divide the probabilities by the temperature. So these are only 3 values, but the point is that the higher temperature you use, the more diverse captions you give, which leads to better accuracy. Again, they also do a comparison with ImageNet descriptions. So ImageNet descriptions are derived from WordNet. So WordNet database. So it's using those captions. And the second one is the standard image prompts generated using definitions of each ImageNet category already in the database. So again, still using GPT-3 still gives the best accuracy. So that's it. So the conclusion is basically that leveraging knowledge from LLM can immediately improve zero-shot image classification accuracy, and CuPL which uses GPT-3 or any other LLM, requires less hand engineering efforts. And these prompts can be customized to the desired categories. It lowers the barrier of prior knowledge about the data set, and there is no additional training. So that's a big advantage and completely remains zero shot. Thank you.
Awesome, thanks, Sathvik. Aman, you want to hit stop recording there?